Recursive functions are defined by their ability to call themselves, typically with a condition that leads to termination. The factorial example that you see on your screen demonstrates a classic use of recursion. The function factorial n calculates the product of all integers up to n. It uses a base case, that is, if n is equal to 1, to end the recursion. When n reaches 1, the function returns 1 as the factorial of 1 in itself. If n is greater than 1, the function calls itself with n minus 1, multiplying the result by n until it reaches the base case, which is n is equal to 1. This process effectively stacks each call until the base case is met, then unwinds, multiplying the numbers together to get the factorial. The factorial function elegantly demonstrates this recursion process by calling itself with a decrementing value until it reaches the base case. Regular functions struggle with this pattern because they would require maintaining and updating an external counter or accumulator through iterative loops, making the code more verbose and less intuitive than the recursive approach, especially for mathematical computations that naturally follow a recursive definition. This recursive function calculates the nth Fibonacci number, a sequence where each number is the sum of the two preceding ones. This sequence is also observed in nature. The function Fibonacci n checks if n is less than or equal to 1, in which case it returns n itself, covering the first two Fibonacci numbers 0 and 1. For values of n greater than 1, it recursively calls itself for the previous two positions, that is Fibonacci n minus 1 and Fibonacci n minus 2, and sums their results. This recursive calling continues until it reaches the base cases, effectively building the Fibonacci sequence from the bottom up. This recursive function computes the nth Fibonacci number, a sequence inherently recursive in nature. Regular non-recursive approaches would necessitate iterative constructs such as loops and manual tracking of previous sequence values to calculate the next one, complicating what is conceptually a straightforward recursive pattern. This added complexity can obscure the natural simplicity and mathematical beauty of the Fibonacci sequence. The SUMList function showcases recursion applied to list processing. It sums all elements in a list by recursively adding the first element of the list to the sum of the remaining elements. The base case for this recursion is an empty list, if not first, which returns 0, indicating there is nothing left to add. If the list is not empty, the function takes the first element and adds it to the result of a recursive call to itself with the rest of the list. This process repeats until the list is empty, at which point all the additions are combined to produce the total sum. The SUMList function uses recursion to sum elements of a list by repeatedly adding the head of the list to the sum of the tail. In regular iterative functions, summing elements would typically involve loops and an accumulator variable to hold the sum as you iterate through the list. While effective, this approach lacks the elegant simplicity of recursion, where the function structure mirrors the conceptual breakdown of the problem into smaller manageable parts without the need for explicit iteration or accumulation logic.